All right, so please, two things. If at any point you stop hearing me, please let me know. You can type in something on the chat or just say something. You can also use the icons to raise up your hand or do something of that nature. So I'm minimizing the window so I can't actually see anybody or hear anybody except you speak up or type in. All right. Yeah, so the building was good. I know that some of you might be able to cope with that, but yeah, finding difficult dealing with code. So, and I know that a couple of us also have the census near us. I said to record this. I think it will be better for us. By next week, everything will come back to normal and we'll get back to our class. Okay? All right, so we're going to continue with hypothesis testing. We started this last week. Last week. I hope you had a good break. I hope you are much more refreshed. I know that the last content confidence interval was a little bit more tedious than what we used to do before now. So if you still find anything difficult there, like not just that, any other contents, just walk through the question, send me a snapshot of the question, and send me a snapshot also of your solution. That way I can see what you did, I see your attempt, I see where things may have deviated, and then point you to the right direction. You'll be able to get better and specific back that way, instead of just a blank email that's, like that content is not clear. That's not very helpful to both of us. Yeah. All right, so we're going to continue with hypothesis testing. This section also has a list of things to pay attention to, and I will be illustrating that with the worksheet that I already posted. Okay, and as before, the PowerPoint, I hope you know where to get them. The PowerPoint and the slide we are using are all on the website. Sorry, something is flicking over. Yeah, so the PowerPoint and the slide are on the units website, and the worksheet we're going to be using are also there. So I'm going to be picking them up when the time comes. Okay, so we get back here. Let's go from the beginning. A quick review of what we did. A hypothesis test is a claim, right? A statement about a property of a population, right? So if somebody claims that certain value exists in the population, the only way you could actually verify that is through hypothesis testing, because you can assess everybody, as we have said over and over again. So if, for example, somebody says the median income in the country is $50,000, there is no way for you to know that, except if you track everybody down and find out how much they earn, and that we know that will be very tedious and difficult. So by hypothesis testing, we can take a sample, and through that sample, if it is representative enough, through that sample, we can actually verify whether that claim is true or not to some degree of certainty. Okay, and that is hypothesis testing. So we have the claim, and then we have the test as a procedure to verify that claim. Okay, and we talked about having the null hypothesis and the alternative hypothesis. And the null hypothesis is simply a statement that the claim is true, right? So if someone says on the average, everybody has 120 heartbeats per minute. The null hypothesis here is that yes, that will be true, and it will be written or represented as H naught is that the mean heart rate is 120, and that is the way it is written, right? So what will you do when you are doing hypothesis testing is either to design a test to either reject or fail to reject, right? And we did make emphasis that we don't accept. We either reject the null hypothesis or we fail to reject it, okay? And then opposite to that is the alternative hypothesis. So whenever you reject the null hypothesis, then you must agree with the alternative. And the alternative is saying the opposite of what the null says. So if we continue with our heart rates of 120 for the entire population. If the null hypothesis says that everybody's heart rate is 120, then the alternative could say one of three things, right? The alternative could say it is not 120, right? That is, it is not 120. This is just saying, it could be less, it could be more, but I'm saying it's not 120. And then the alternative could also say, with all here, the alternative could also say, it is less than 120, right? If that is what you believe. And a third alternative could still be that it is more than 120, right? So these three are different alternative hypotheses, right? But only the first one, this is the null. So you see, there is only one way null hypothesis could be stated, right? But there are three ways the alternative could be stated. So part of the sources for answering question on this section will be to kind of figure out which of the alternative is the question presenting to you, right? The null is presented only one way as we have it here, but the alternative could be presented either of these three ways, right? And the way it is presented depends on the parameters you use in solving it. So for example, the first one, let me change the color. Okay, let's see. Okay, that one. So for example, the first one, the first alternative is a two-tailed test, right? Because you're saying you don't know either way, right? But the last two alternatives are all one-tailed. Yeah, both one-tailed tests. So, and we explained before that here you use your alpha over 2 or two-tailed test. But if it's one-tailed test, you use, excuse me, all the alpha in answering the question. We're going to see that in a moment. Yeah. So this is just a kind of quick review of the things we did, and I think I should go through the remaining clip as well. Just a quick review as well, seeing every other thing. So here, let's see if I can. A moment, let me remove all this. Okay. Right, so here, we could conduct a right tail test, which means we are questioning the hypothesis on the right tail, right? And as we said, all of the alpha will be used because this is a one tail test. And the critical value you'll be looking for will also be one critical value. And it will be positive, right? And then here we are doing a left tail test. This is also a one tail test because we're just on the left. All of the alpha will be used here. And we're going to have just one critical value as well. And this will be a negative critical value. And I'm using Z here for illustration because this could also be a T. So this could also be a T alpha, right? And the previous one could also be a positive T alpha, right? Depending on whether you have the population standard deviation, right? Whether you know this or not is what tells you whether to use C or T, okay? And then finally, it could be two-tailed, and whenever it's two-tailed, and take note of the alternative hypothesis in both cases. In all the instances, the null hypothesis is always the equality sign. But when it is two-tailed, the alternative says not equal to, right? And if I should go back very quickly, when it is one tail on the left, it says less than. The alternative will say less than. And when it is one tail on the right, the alternative says greater than, right? So from the alternative, you can actually tell the type of test you are conducting, but in practice, this is not always written as symbolic. It could be stated in words, so you pay attention to that. And we're going to take an example to illustrate that later today. Okay. So as noted earlier, so this is a Z. It could also be a T test, depending on whether you have your population standard deviation or not, right? So if population standard deviation is known, you are using a T. If it is not known, you are using a C. I'm sorry. If population standard deviation is known, you are going to be using a Z. If it is not known, then you are using a T. Okay? All right. So these are the three tests we can conduct in hypothesis testing. Still a quick review. So last class we talked about this. So we've been talking about alpha, and this is the actual definition. I'm going to work some concept questions to illustrate that before we go into solving an actual question today. So here, significant level is what alpha is. So alpha is the significant level. And significant level is simply the probability of rejecting or wrongly rejecting the null hypothesis, right? When it is actually true, okay? So you have your diagram this way, your distribution this way, and we know we take a confidence interval. Let's assume I'm doing a two-tailed test. Then I am 95% confident that the answer is true if my result falls within the middle region. But if my result is on the tail here or here, then I'm going to reject. And this tail is what you refer to as your alpha, right? So it is the area you're willing to say, no, the null hypothesis is false. It's the area where you're willing to say this is false. And then you support the alternative. Okay, I'm going to go further on this. And as we saw last week also, this is known as type 1 error. And we'll review type 1 and type 2 error very quickly. Okay. So whenever the null hypothesis is rejected, it means you have sufficient evidence to support the alternative hypothesis. That's what it means, right? So if I'm saying, for example, that H0, the average height is not 5 feet, if I say this is false, then it means I am supporting the opposite, which is the alternative, right? And we know, of course, the alternative could go in 3 ways. It could be that I'm saying the alternative is that it is less than. It could be that I'm saying the alternative is that it's more than. It could be that I'm saying the alternative is that's not equal to 5 feet. So whichever one it will be out of this three will be contained in the question. Okay, we'll pay attention to the question to know that. So whenever we reject the null hypothesis, it means we have evidence to support the alternative. Okay, and conversely, if we fail to reject the null hypothesis, it means we do not have evidence to support the alternative, right? So it just goes both ways. So if you reject, it means you have evidence to support the opposite of the alternative. That's why you're rejecting. If you fail to reject, it means you do not have enough evidence to support the alternative, and that's why you fail to reject. So these are just like basic concepts, right? And so we talked about type 1 and type 2 error. And we said type 1 error is if you reject the null by chance, when actually it is true, then you've made a type 1 error, right? Because this could happen, and remember that we are constructing our test based on the confidence interval. So if your confidence interval is 95%, as traditionally is, generally, then it means that you are accepting that sometimes your answer might actually be wrong. Sometimes your answer might fall on this tail, right? So if your answer falls on the tail, then you are willing to accept that percentage error there, right? The alpha, which will be shared into 2 in case of two-tailed test, is actually the same thing as your type 1 error. We saw that earlier, right? So type 1 error is the same thing as alpha. It's the probability of rejecting the null hypothesis when it is true. Okay, we'll have some concept question to illustrate this further. Then type 2 error is the opposite. Okay, if the null hypothesis is false and you fail to reject it, then you've made type 2 error. Okay, and symbolically, type 2 error is written as 1 minus beta alpha, right? Sorry. So they act in the opposite way. It's actually denoted as beta. Okay, so it's 1 minus alpha. So we see that there are trade-off between these two. If you increase one, the other one decreases. If you increase alpha, beta decreases, right? If you decrease alpha, beta increases. So they act in the opposite direction. So it's a trade-off. Do I have a risk of rejecting the null? Is that a problem for me in this case? Or do I have a risk of failing to reject the null? Is that a problem for me in this case? For example, to reject the null that the drug does not work is to say that the drug works, right? So that could be a different risk from to reject the null that sales will not be up to a certain amount, or to reject the null that a certain number of patients will not come to a clinic at any point in time. Okay, so the fact that patients will not come, that is not, there's no high risk there, right? Compared to the fact that you are saying a drug is effective when actually it is not, right? So depending on the risks, we tend to adjust type 1 and type 2 error accordingly, okay? And we get to do some concrete example to illustrate this. So I think these are the areas we covered last class. Again, let me find a way to clean up the slide. Okay, so these are the kind of few things we covered last time. And then we stopped at just moving beyond this point, approach to hypothesis testing, right? So we can approach hypothesis testing in two ways. One is by using p-value. I think I can hide this so I could see what I have over there. Yeah. So one is by using critical value and the other is by the p-value method. Again, we're going to take questions focused on the p-value method today, if time permits. But generally what it's simply saying is, for the critical value method, your critical value is the points that, where the cutoff is here, right? And this area here is your alpha. Okay, so the critical value is the point that marks the end of where alpha stops, if you want to shade in alpha, okay? And so what you're trying to do is to use your table to get your critical value, your either Z statistics or T statistics, depending on which test you're conducting, right? Depending on whether you know the population standard deviation or not. If you know the population standard deviation, then you're doing a Z. If you don't know that, you're doing a T, okay? We're not using the sample side, we're using population standard deviation as our measure of when to do Z or T. So again, if you know the population standard deviation, you do a Z. If you don't know the population standard deviation, you do a T, okay? So depending on which, the nature of your question, you use the table that we are used to already to get the critical value. And that is the point that marks the end of where alpha stops. Okay, and alpha is the area shaded in on that. I'm using one tail test to illustrate this to make it easy. Okay, and then after you got the critical value, the next thing you do is to compute the test statistic, right? And again, your test statistics will be either a Z or a T, and it will be aligned with what you did in critical value. So if you did Z on critical value, you're going to do Z on your test statistics. If you do T on critical value, you're going to do T on your test statistics, okay? And so once you've done either Z or T, as the case might be, your critical value, you also do either Z or T in your test statistics, you go ahead and make your decision. And this is how to compute your test statistics. If it's Z, you're computing with this. If it is T, you're computing with this, right? And I'm sure this formula is already familiar, isn't it? We've used this for some time. And the difference between them is just that in place of the population standard deviation, we now have a sample standard deviation in the T space. Okay. All right. So this is what you compute your test statistics with. But remember, don't mix this up. Don't confuse this with the Z equal to data minus the mean divided by standard deviation. This is the Z score, right? The test statistics has a little difference in the formula on the denominator. Okay, so you want to know when you're looking for just your Z score, which we did, I think, in chapter 3 and 4, 5 and 6 or thereabouts, and then you want to know when you're looking for your Z test statistic. The test statistics has a different formula. Okay. All right. And once you've got your critical value and you've got your test statistic, then you then compare the two. Right? So you compare your test statistics with your critical value. and make your decision. For p-value method, you do a different comparison. Okay, so let's talk over on p-value method. Any question on critical value method? Okay, so this is a little bit different because unlike before, I could see your faces or see the class to see your gauge your understanding. So if you have any question, just stop me just speaking or do a chat, okay? And I will be able to pick that up. All right, so let's continue. So if that is critical value, and when we solve question, this will become clearer. Let's move on to this side to look at p-value. On p-value, I want you to take note that you also have, and I want to change this color to blue. Take note that you also have an area here, right? And if you look at this area, it's very similar to the area we have as alpha on the other side, right? But this is your p-value. And how do we know it's p-value? We know it's p-value because the point here where it stops, that is your test statistic. So for critical value, for alpha, that point is critical value. But for p-value, that point is your test statistic. Okay? So p-value is calculated using your test statistics. And once we are done with that, we compare the p-value with alpha to make a decision, right? We compare alpha with p-value to make a decision. But if you're using the critical value method, you compare test statistics with critical value. Okay, and I know that at this point, this might be, sounding similar or true, but once we start doing actual calculation, I believe it will be much more better. So the summary of what I've said so far here, and you could look at this video again to get clarity, is that the critical value method or the p-value method is used in making decision and hypothesis testing. Okay, so today we're going to focus on p-value method. And next class, we'll look at the critical value method. Okay. So whenever you make your decision, okay, so after you've made your decision, either with critical value or p-value method, then you do your rejection just the normal way, right? If you're using the critical value method, if the test statistics, right, is within the rejection region. So you have your rejection, you have your map this way, and then this is your rejection region, the area where you have alpha. Okay, it could be two tail, it could be one tail, but assuming it's one tail this way. If your test statistics fall somewhere around here within the rejection region, then of course you reject, right? If it didn't fall here, if it falls somewhere in this white region, then you fail to reject. Okay, and this is just for one tail test. If it is two tail test, then you have the two tail marked out. So you now have two rejection regions. This spot here under the shaded area and this spot here, right? Then your failing to reject will be if your test statistics falls within the region here. Okay, that's how you make that decision. But for p-value, you compare p-value with alpha. Okay, so when you collect your data, you normally set up your alpha. Remember, alpha is the chance of making type 1 error. So if I'm doing a left tail test, I could say, hey, I want to reject, I'm allowing a 5% mistake in this research. Okay, so you go ahead and collect your sample. And after you collect your sample, then you plot your distribution again. So let's say this time, this is our distribution after collecting the sample. Okay, so remember that when you do alpha, you calculate your critical value here. That will be the point here, right? And then when you collect your data, you calculate your test statistics. So this could be a Z test statistic, or it could be a T test statistic. So once you do that and calculate that value, that is the value here. With that test statistics, you can find this shaded area. And this shaded area is your p-value. Right? Remember, the one shaded on red, I called it alpha. Let me change that to red. This is your alpha. Okay, and again, the difference is that for your alpha, the bounding point, what tells you the demarcation where it ends, is your critical value. Okay, but for p-value, what tells you where it ends is your test statistic, either T or Z. And that's what they're so. But alpha and p-value, both of them are area. And that is why, after doing your test, to make your decision, you compare your p-value with alpha. Okay. The general rule is that if p-value is smaller than or equal to alpha, you are going to reject the null hypothesis, right? That simply means if I take out this shape now and superimpose it on this one, if my p-value falls in between here, so my p-value is smaller than alpha, which means if I shade it in, it will be, it will be contained inside the red area. And that means it is still within the rejection region. And that is why you have to reject, right? But the opposite is the case. If p-value, assuming the shaded area in blue is actually bigger than the shaded area in red, so if p-value is bigger than alpha, what will happen is that if you superimpose this on this shape, you are going to have this area cover all the red shaded area in blue, but because it's bigger, it's going to cover that and come inside here because it's bigger. And once it comes inside here, it has entered into the non-rejection region, the white space. Then you fail to reject. Okay, so this is the alternative decisions we are making to make a decision about the hypothesis test. So any question at this time still? Okay. Okay, so just to be sure that you are hearing me and you are seeing my screen and everything, can you type in yes? If you're seeing the screen and following what we're doing so far. Okay, at least we have one person. Okay, okay, good. Okay, thank you. So this could be very anonymous because I can neither see anybody nor hear anybody. Okay, so the explanation so far again might look very similar and the terms might still be all over the place, but what I would suggest you do is watch the video again, and the video we recorded for last class, also look at it again, right? Because it's important to get these concepts in. Once you understand the concepts, applying them in solving the question will be less tedious, right? But if the concept is misunderstood, when you're asked a question, it will be difficult to kind of know how to approach it. So the study method here, or the study skill here, strategy here, will not just be to memorize the formula or to remember the steps. It will be to know the concepts, right? So when you know the concepts, you are able to more effectively apply it to solve a given problem, okay? All right, so let me see, I don't know why this is not clear. Let's go ahead and see, let's go ahead and look at some actual questions, because this is really the end. So in summary, what you do in hypothesis testing is these 6 steps. Okay, the first thing you do, of course, is to look at your null and alternative hypothesis, right? And if you're the one conducting the research, it's your duty to state that. So you state your null and alternative hypothesis. And after you've settled on that, decide on your significant level. So upfront, say, I'm going to use alpha as 5%. I'm going to use alpha as 10%. So that means I'm allowing that this research could make a mistake of 5%, or there could be an error of 10%, depending on what you are doing. The higher the risk, the lower the error you will allow, right? And then after doing that, the next thing is to collect your data and then compute your test statistics. Once you compute your test statistics from the data, and it could be a t-test, right? If you don't know the population standard deviation, or it could be a z-test. if you know the population standard deviation. Now, you remember the formulas for these things, right? So we know that our t-test is giving us your mean minus the population mean divided by standard deviation, sample standard deviation, all over square root of n, right? The same thing happens for the z, just the standard deviation changes. So for your z-test, you have the sample mean minus the population mean divided by population standard deviation over square root of n. So once you compute your z or t-test statistics, then from that you can get your p-value. Now we're going to be using Excel to do the p-value today. So when you compute your p-value, then the next step is to make your decision. Do you reject or do you not reject? Right? Another way of saying not reject is to fail to reject. Right? So you make that decision based on the p-value. And what you are doing is to compare the p-value with alpha, the alpha you chose on step 2. So if the p-value is smaller than or equal to alpha, you're going to reject the null hypothesis. But if p-value is bigger than alpha, then you're going to fail to reject. Okay? And then, of course, you interpret your results in the context of your question. And we're going to be taking examples to illustrate all these steps. Okay. All right. Any question or concern at this time? I'll discard that. Okay, so let's go to the slides and start with the some of the conceptual questions we were working on last time. Let's look at a few of them, and then we go ahead and solve some questions. And I think there's no problem. So let's look at this first, and then we go ahead and pull up the other worksheets to solve some questions. Okay, so you're going to be typing in your suggestions or your suggested answer, or you can speak out as well if you wish to do that way. So let's look at question 1. It says if the p-value is 0.03 and the level of significance alpha is 0.05 in a hypothesis test for the mean. It says then we accept the alternative hypothesis. Okay, so this is like saying, remember how to make this decision. Right? Remember we compare p-value with alpha. And if p-value is less than or equal to alpha, we reject the null hypothesis. Okay? If p-value is greater than alpha, we fail to reject. And by the way, accept is not, it's just the way this worded that, the textbook worded that, but accept the alternative is not the right statement. So accept the alternative is something as failing to reject. Okay, so you can mentally replace those two. But in reality, we don't. Oh, okay. I think we actually accept the alternative. So that is okay. That is okay. I think I'm reading that wrong. Just a moment. Let me correct that. So that is not right. So it's the null that we don't accept, but you can accept the alternative. Right? So accept the alternative here will mean the same thing as rejecting the null. Right? Because when you reject the null, it means you accepted the alternative. So let's go through this question again and type in what you think is the correct answer. It says if p-value is 0.003 and the level of significance is alpha is 0.05 in a hypothesis test. So the question is suggesting then what we ought to do is to accept the alternative hypothesis if this is our finding. So what do you think? Do you think this is true or false? You can type in. Okay, let me see what I have here. Okay, false. Thank you, Brennan. Can we get more suggestions? And don't bother about, okay, we actually have some more there. Colin, you said yes. So true, I believe that is what that means, right? Okay, Brenna, your answer changed. Okay, so can we get more people respond? Just say what is your feeling about it. Don't bother about whether your answer is correct or wrong. I think there is a poll here. Maybe I will be using that so that everybody can be sure to respond. But just type in what they think. Don't worry about the correctness. We're trying to pick up the consensus. All right. Okay, let's go with what we have and just try to look through the question. So what you do is focus on that decision, right? Remember what we have on the slide. So ask yourself, is the p-value less than alpha? Okay, so let me pick up right here. In this case, we are looking at p-value and we are asking whether it is less than or equal to alpha, right? So the p-value here is 0.003, and we are comparing that with alpha of 0.05. Okay, so which one is bigger here, or which one is smaller? P-value is smaller or alpha is smaller? You see your charts. Okay, we also have people terminating true. Okay, true. Okay. Okay, so we look at this. So we see that p-value here is smaller, right? So actually this expression is saying true. Okay, so p-value is actually smaller here. So, but what about our decision? Whenever p-value is smaller than alpha, remember what we do is to reject the null hypothesis, right? And so, and whenever you reject the null hypothesis, it means you are accepting the alternative, right? So if you reject the null, you accept the alternative. You reject the null, you accept the alternative. And you reject the null when p-value is smaller than alpha, smaller or equal to alpha, you reject the null. So if I have had 0.05, 0.05, I will still reject the null. So equal or less. Okay. But whenever p-value is bigger, then you fail to reject the null. Okay. All right. So the answer here will be the first one. It will be true. I mean, the second one, it will be true. And that is what we're supposed to do, because if p-value is smaller than alpha, then we should reject the null hypothesis, right? And if we reject the null hypothesis, it means we are accepting the alternative hypothesis. Okay, so that question says true, or that answer is true. Let's look at the second one. Suppose a sample size of 103 was used to conduct a left tail test for a single population mean. The null hypothesis is that the null hypothesis is that the mean is 22. After computation, the p-value was found to be 0.04. Okay, so this is kind of asking for the interpretation of what p-value means. So the question says, if that is the case, if p-value is 0.04, then there is a 4% chance that the population mean is equal to 22. Right? There's a 4% chance that the population mean is equal to 22. Okay, let's talk through this very quickly. So what they're saying is that, or what this question is trying to do is to define p-value. So it's defining p-value as this. Okay, but that is not the definition of p-value truly, right? P-value is the chance of, remember what it is, p-value is the chance of, okay, so I don't think I actually defined this in any way. Okay, so I'm going to add up a slide to that PowerPoint. I'll post that after class. Okay, p-value is the chance or probability of getting a test statistics value as extreme, okay, the spelling of extreme, or more extreme than the value we got. Okay, I'm gonna put a slide to add this definition, and you can also Google it online and see that, but I'm gonna put a slide with the formal definition, okay? So what this is saying is, if I do my test statistics, if I get my data and compute my test statistics, let's assume I'm doing a left-tail test, as this question said, and then this is my test statistics over here, okay? And so if this is my test stats, then this is my p-value. The area to the tail of the test statistics is my p-value. So the p-value is trying to tell you the chance, because this will be in percentage eventually. So in that question, this is 4%. So the p-value is trying to tell us about the probability or the chance that our answer, the test statistics value we get, will be as extreme as this. Remember, it's in the middle. I mean, this is the population mean. The typical answer will be here. So what is the chance that our test statistics after we collect our data will be as far as it is here or further, right? Because if the test statistics is anywhere around here, the results are the same. Whether it's here or here or here or here, doesn't matter. Once it falls into this shaded region, then the result is the same. So the p-value is trying to measure the probability that that test statistics is at this point or further than this point. So it's extreme or more extreme than the value we actually got. Okay, so I will add a slide to kind of formally define this. So in essence, the answer to this question is false because it is giving us a wrong definition of p-value. Okay, I think I should use a check mark to be consistent. Right, so the answer to this question is false. Okay. All right, let's continue. Let's go to the next question. And I think we might end up skipping some of them, but let's see. Okay. So for the next one, any question on this one we just covered? Okay, I'll add a slide to define that p-value. It's an omission. Okay, so for the next question, it says a researcher hypothesized, no, not that one. I see. So the check mark is moving with us. So the answer to this is false. So we're going to the next question here. This is number 1, number 2, we're going to number 3. So for question number 3, a researcher hypothesized that the average students spend less than 20% of their total study time reading the textbook. Says the appropriate hypothesis test is left-tail test for the population mean. So reading this question in this context from what we have done so far, do you think this should be a left-tail test, or this should be a right-tail test, or this should be a two-tail test? Okay. And the hint here will be, you are imagining your diagram, right? And you are thinking about what the test is trying to do. Okay, so this here will be the average time it is assumed students spend reading textbooks, right? Okay, so 20% of the time. The question will now be, reading this here, do you think this researcher are you going to be testing that time is less than this? So the null hypothesis is that the average time here is 20% of the total time the students have, right? So the question is saying, this person is going to test whether that study time is less than 20. So your alternative hypothesis is saying that average time is less than 20%. So what we are saying here is that this here represents a left tail test. Is that true or false? Okay, so let me get your answer. True, false, no response. Okay. Again, when we do this thing, don't worry about the answer being correct or not. Okay. Just say what comes, and the more you say what is in your mind, the more active and engaged you become in the class, because then you get clarity in your own mind why your answer might not be what it is. Okay. If I'm taking, I don't know, there's so many. Okay, so I'll take it. Everybody who responded says true. Yeah, so that is true. That is true. So look out for the keywords here. Less than. When it says less than, it means this person is concerned with checking that it is on the left tail. When it says more than, then the person is thinking about the right tail. And the alternative hypothesis in this case will be this way. Okay, so essentially the alternative hypothesis points to the type of test. Okay, so if it's greater than, more than, then you are going to the right. The arrow, the inequality expression is pointing to the right, going to the right thing. If it's less than, then you are going to the left thing. Okay. Then watch out for the expression where it will say not equal to. Okay, I guess we might see it here, or we may see it in the actual question when we start solving. Okay, let's move ahead and look at the other ones. So I'm going to skip some of this so that we can have time to solve some more questions, and you have time to practice with this on your own work. Okay, let's look at type 1 and type 2 error. I think they are the last two questions we have. Okay. Moments. This is a little bit more detailed than this. Okay, so let's look at this practice with type 1 and type 2 error before we move on to solve other type of question. Let's look at this question here, the first one. Okay, let's look at this. It says 2011 survey by Bureau of Labor Statistics. I think we did this last class, but let's go through that again. 2011 survey by the Bureau of Labor Statistics reported that 91% of Americans have paid leave in January 2012. Okay, a random survey of 1,000 workers showed that 89% had paid leave. Okay, so this is a data reported, and the question, after reading through all this, right? Okay, so the p-value was this, right? And we are doing and the alpha was bigger than that, so the null hypothesis was rejected. Okay, so it was concluded that there was a decrease. The question is, what type of error is possible in this situation? Okay, and I went through this to save us time. So essentially, what you're focusing on here in this type of question, because all these are just giving you context, and you don't really need any of them per se to solve the question here. The critical information here is that the p-value is that the null hypothesis was rejected. That is the critical information. Okay, so it says if the null hypothesis is rejected, what type of error is possible in that situation? Okay. Well, very quickly, let me go to the slide. I think that will help us better there where we define. Look at the definition of type 1 and type 2 error. Okay. Type 1 error is rejecting the null when it is true. Okay. Type 2 error is not rejecting the null, or somebody can also say failing to reject the null. Right? Not rejecting the null when it is false. So whenever you reject, you have created opportunity to have made type 1 error. Whenever you fail to reject, you created opportunity for possibility of type 2 error. That is just the way it is. So when you're reading this kind of question, that is what you pay attention to as a guide to the answer. So if you look at this question, because it says here that the null was rejected, right? So if the null was rejected, then we only have the probability of making a type 1 error. Because you can only make type 2 error when you fail to reject the null. Okay, so that is the key to answering questions like this. Let's look at the next one, and it's very similar. Okay, so here again, you can read all this and get comfortable with the context, right? But it says here, food inspectors inspect samples of food products to see if they are safe. This can be thought of as a hypothesis test, right? The following is an example of what type of error. The sample suggests that the food is not safe when it is actually safe. And it has told you what the null hypothesis is. The null hypothesis is that the food is safe. Right? And then, but the sample they took suggested that the food is not safe. In essence, the null was rejected. The null that it was safe was rejected, and they accepted the alternative, which is saying it is not safe. Right? So again, there was a rejection down here, and this will also be a type 1 error. Okay, all right. So it's unfortunate we didn't have type 2 error on the sample here, but the type 2 error will be like a scenario. Assuming this question says, if I strike this off, and this question says the sample suggests that the food is safe. Right? When actually it is not safe, right? But it's actually, it is actually unsafe. Right? So this will be a type 2 error. Because if you say the food is safe, it means you are failing to reject the null. If you say the food is safe, you are agreeing with the null because the null says the food is safe. So if you agree with the null, it means you also fail to reject the null. And whenever you fail to reject, you have a possibility of a type 2 error. Okay. So you go through this video again and see what we did last class, also explaining type 1 and type 2 error. And I also have a chart here that could also help you kind of make sense of that a little bit. Okay. So this chart here from your notes. So whenever the test, so here is the statistical test. Here is the statistical test, right? Whenever the test agrees with the reality, right? If it agrees with the nature of things, the true nature of things, if they agree, then there is no problem. And that happened in these two quadrants. Here, the nature of things is true. The test accepts that it's true. So there's no error here. Here, the nature of things is false. The test also accepts that it's false. There is no error here. But here and here is where you have the type 1 error, right? Here, the nature is that it is true, right? It's true here, but the test rejected. So that was done in error. So that's your type 1 error. Whenever you reject, right? If you reject the truth, you made a type 1 error. So over in this last quadrant here, the nature is false, right? But the test failed to reject, or in other words, accepted that falsehood. So that is also an error. Okay. So I hope all this input together will give you some hints. And if you have any specific question, you can send this over. Okay. All right. So any question at this time? Okay. So again, going through this video over again will be a good thing to kind of try to get these concepts more settled in the mind. But it's not something that happens automatically, right? You have to take time to practice on it, to get it more settled. And we're going to solve at least one question here to kind of push down knowledge further down. Okay? Make the knowledge kind of more settled. we start with second question, because that will take less time. Or maybe we should do the first one. Okay, so let's go ahead and do the first one first. Okay, so over here, this is like maybe the most complex of the questions you could get, so I'm using it as an example. It's very similar to what we did on the confidence interval test, right? Okay, so you help me with your calculator here so I will work very fast and get this done before time. Okay, so this is the scenario. This is scenario, and this is an actual hypothesis test, right? It says average American gets a haircut every 39 days. Okay, is the average different for college students? And that's the question here. Okay, so from this, you could begin to pick up the hypothesis. Okay, so to verify whether that average is different, the data below shows the result of a survey of 11 college students, asking them how many days elapses before a haircut. Okay, assume that this is normally distributed, right? This is telling you that so that you can use your normal table or you can use your t-table. If the alpha is set at 0.10, significant level, the question then is, for this study, we should use what type of test? So if you drop down this arrow, it should be asking you whether are you going to use a t-test or a z-test. Okay. Can you suggest to me which one you think we should be doing here? Should this be a z or a t? Oh, I can't see your chart. Let me see. Can you all see this stuff? I think something is indicating on something here. Can you all see my screen? Okay, I'm missing the Zoom holding point here. Where is that? Okay, let's minimize this. Okay. Okay, I'm missing the handle for this. I haven't had this happen before. Okay. That's quite strange. But can somebody speak out and tell me if you're seeing my screen? Where I'm working here, let me pull up this again. Another one. Yeah, this one. Can you all see the hypothesis test here? Can somebody speak out? I can't see your chart anymore.
Yes.
Hello, can someone say something? Let me be sure that I can hear you, that this is properly connected. Okay. I see a lot of chats. Yes. Okay, you can see my screen. Okay. Somehow I lost the handle for what I'm doing here. I sincerely don't know how that happened. So I'm going to stop sharing and share it again so that way I will be sure that everything is okay. Okay, so I think you can see my hypothesis testing here. Then let's continue. I've got the handle back. All right, so the question was, is this a t-test or a z-test? The illustration here. Can you chat, even if you typed the answer before, can you type in again? Should we be testing a z or a t in this case? Okay, McKenna, you said a t. What would be your reason for suggesting a t? Would you add a little more information? And any other person have any other, no standard deviation, okay? Okay, so that is correct, but I would say no population standard deviation, right? Okay, thank you for the response. So yeah, so no population standard deviation. So that's what you're looking for. And if the test doesn't say, the question doesn't say the word population, of course, it means you don't have population standard deviation. Okay. But we know we can get a standard deviation from this, but we can only get a sample standard deviation, not the population. Right? Okay, so let's quickly solve this. So the biggest thing to calculate here is actually just the standard deviation itself and the sample mean, given this data. So let's see if we can accomplish that before the time runs out. And help me as quickly as possible. And if you can speak in, that would be better. So I don't have to be pulling the chart out. So we have our data here, and then we have our data minus the mean here squared. And then we add that up to get our standard deviation. So let's see how quickly we can do this. What will be the mean value here? Let's go ahead and do that. So we have 48 plus 26 plus 40 plus all that. Let me pull up the calculator. I think that might be better. So we all work together. Okay. I hope you can see the calculator. Right. So here okay, let's see if you can decide. We are trying to do we're going to do 40 plus 26 plus 40 again plus 44 plus 38 plus 35 plus, and you can be working this also, right? 31 plus 39 plus 46 plus 38. Right? We got 337. 377 rather. Okay, so we're gonna assume the mean, the sample mean will be given us, so let's have it here. The sample mean will be given us the sum of the data divided by how many they are. Now we got 377, and we know there are 11 data points. So we divide this quickly. 377 divided by 11. So divided by 11, and we got 34.2727. Okay, maybe we'll keep it at that. So we got 34.2727. So we got 34.2727. Anybody got something different from this? Okay. But if you're following me, I believe what worked is correct. And what is important here is just to follow the procedure. If we miss something wrong, we'll be able to maybe figure it out if we calculate properly. And maybe we can do this quickly again just to be sure. Not sure we have enough time to complete this question. Okay, so what I'm going to do for sake of time, I think next class we will deal with this one. This is 33 minutes. Okay, so what I'm going to do for the sake of time is to solve the next question, not this one, so that we can at least get something concrete on this aspect so you can start your homework on that. Okay, so what we would have done here is to find the mean, right? And we got this to be 34.2727, assuming the working we did quickly is correct. And then you find the sample standard deviation. And once you get that, since we agree this will be a t-test, you go ahead and compute your t-test statistics, okay? But let's leave that and go to the one where the mean and the sample standard deviation is already given. And then we can work on this one next class. But what we're going to do with this question, you should be able to solve the first one. Okay, so in this one, we already given the values we need, right? It says the average salary for American college graduates is 43,800. And you suspect that this average salary is less for graduates from your own college, right? Okay, so let's quickly map this, save time. So the theory is that the average salary in the population is 43,800, but you are suspecting is less. So you are testing the left tail. Okay. The previous question that says here, you think it is different. This is testing two tail. Okay, so from the question you can figure out whether you're doing one tail or two tail. So here we are testing less and we're testing the left tail. Okay, so you selected 56 students randomly and you found out that the average salary was 43,037 and the standard deviation was this. Again, notice that the population standard deviation was not given to us, so we're using T. What can you conclude using the alpha? These are the breakdown of the test we're supposed to do. So the first thing here is that we're using the t-test because we don't know the population. Okay. The next thing here, the null alternative hypothesis. We know the null hypothesis. If you drop down this arrow, you see a couple of things, but we know that the hypothesis should be here. So we get the null. Okay. And the null is saying that the mean salary okay, so I think the options are inverted. Okay, so here we say the mean salary, okay, is equal to, because that is the null, and then you have the value you have there, which is 43,800. That's the null hypothesis. But the alternative you are testing is whether that mean is actually less than, because that's what you're considering in the question. Whether that mean is actually less than that same amount. Okay, 43,800. Okay. Then what we do next is, since we know we're going to complete a t-test statistics, is to calculate the value of the t-test statistics. And we know the formula, right? We saw that earlier. So your t-test formula will be the sample mean minus the population mean divided by sample standard deviation divided by square root of n. Okay, so we're going to do this very quickly. So your t-test here will be the sample mean is 43. So when you take a sample, you got 43,037. But the population is 43,800. Right? You are dividing this by the sample standard deviation, which is 11,310, all over the square root of sample size, and we have 56. Yeah. So let's go ahead and do this together with the calculator. Then let's play this time, this size. So we're going to do first the sample mean, which is 43,037. So we have 43,037, right? Minus the population mean, which is 43,800, right? So on the numerator, we have negative 763. Now let's go to the denominator. I'll suggest you do this in part that way. So for the denominator, we have 11,310 divided by, do I have square root here? Yes, we do. Divided by, okay, so maybe we should take the square root first. I think that might be, okay, divided by, let's see if that works. Divided by the square root of, it takes the square root straight. So we're taking the square root of 56. Okay, so this works differently. So we're going to take 56 and we'll take the square root. 56 is your n, right? We take the square root of that. So we have that. So we have 7.4833. Okay, 7.4833. And we're supposed to divide this by standard deviation, which is 11,310. Okay, so let's do 11,310 divided by that value here. So 11,310 divided by 7.4833. Right? So when we do that, we have that value. Okay. So we end up having here is equal to -763 divided by this value here, 1511. So 1511.3653. 1511.3653. So we have 1511. Okay. We have 1511.3653. 1511.3653. Okay, so let's divide this two very quickly. All right, so here we have, so I'm just going to pick the positive number, and we know there's a negative number there, 763 divided by 1511.3653, and that gives me this value. So over here, we know that the test statistics is 0.5048, right? So we get that the test statistics is equal to 0.5048, right? But this question says, so remember there's a negative sign here, right? So this answer has a negative value here, right? But this question says run to 4 decimal places. Okay, so I say 4 decimal places, but given the answer is 3. So I think that is a mistake there. So this should be 3 decimal places. So if you run this to 3 decimal places, you get, of course, you get the answer we have here, right? So that's the test statistic. Just put in the value. And the difference between this question and the first one is that in the first question, you are going to by yourself calculate the mean and standard deviation. Every other thing will be the same thing. Okay. All right. So let's continue over here. So once you get the test statistic, the next thing is to find the p-value, right? So I'm going to do the p-value with Excel. Okay. Let's see if we believe we have one here. We're going to do that with Excel. Okay. Okay, I believe you can see my screen. Okay, so in your p-value, what you do, calculating your p-value, remember the p-value will be like if I draw this shape like this, and I shade this area because we're doing left test, we know that this point here, which is our test statistics right now, is -0.5, right? That is the test statistics here. And your p-value is this area shaded here. Okay. And we do that and maybe we stop at that point. So how do you compute your p-value? Take this test statistics and use the function in Excel. Now add this to the PowerPoint as well. You put in your equality sign first and then type in t.distribution, and that is coming up. Okay, because I'm doing one tail, I'm going to pick the second one here. This is for 2 tail. So I'm picking this one. So this one right here, this is your 2 tail. T.dist 2 tail. What I need is T.dist 1 tail. So I'm going to pick that second one. Okay. So it says type in 2 things, X and degree of freedom. Our X is your test statistics. So here we got 0.505. Put in your comma. Okay, and then type in your degree of freedom. What's our degree of freedom here? Can somebody type in for us very quickly? What do you think will be our degree of freedom here? Okay, so remember your degree of freedom is n-1, isn't it? So just pick your n and subtract 1. And n in this question is 56, right? So degree of freedom will be 50, okay? Degree of freedom will be 56 minus 1. So 55, right? So go into the Excel. Once you type in that value, type in 55 as your degree of freedom, close the parentheses and press enter key, and it gives you the p-value. So we have here 0.307788. All right? So 0.307788. And that rounds up to the value they have here. Okay. And once you've got your p-value, the next thing you do is to make your decision. So this one is saying compare that Is p-value greater than or less than? It is greater than, isn't it? So our p-value is 0.307788. Our alpha in this question is given as 0.01. So p-value is actually greater than the alpha, isn't it? And then you continue making your decision. Okay. I know we're running out of time, so I'm going to pick it up from here. But from what I have done, you can start attempting the homework. But by next class, we complete working this question and do other things. So before you sign off, quickly type in present here. I will take that as your attendance. Okay, I know I gave one person permission to leave earlier. So just type in present in the chat and then you can exit. Okay. I will see you in next class. Okay. Yeah, if you're still logged on, you can type it present before you exit. Okay, we have 6 people. Okay, 4 of you still remaining. Just type in present and then exit. A shutdown, you will not be able to, that will not be recorded, right? McKenna, are you there? Lines, Clay, Brooke. Okay. I guess you're all out there. So let me pick up what I have here and we're gonna have to broadcast. Yes.